We are looking at sampling distributions and estimators. The key concept is that in addition to knowing how individual data values vary about the mean for a population, statisticians are interested in knowing how the means of samples of the same size, remember SRS, simple random sampling. So how the means of samples of the same size taken from the same population vary about the population mean. That's the idea. And so what we are going to do, we now consider the concept of sampling distribution of a statistics instead of working with values from the original population. We want to focus on the values of statistics such as sample proportion or sample means obtained from the population. And why is that? Because generally speaking, we don't have access to the population parameter, so we have to deal with what we have, which is a sample statistics. All right, sampling distribution and estimators.
Sampling distribution of a statistic. The sampling distribution of a statistic, such as a sample proportion or sample mean, is the distribution of all values of the statistic when all possible samples of the sample size of the same size n are taken from the same population. The sampling distribution of a statistic is typically represented as a probability distribution in the format of a probability histogram, formula, or table. Population proportion P, sample proportion P hat. General behavior of sampling distributions. 1. Sample proportions tend to be normally distributed. 2. The mean expected value of sample proportions P hat is the same as population proportion P.
So we don't have access to the population, so we deal with the sample statistic. As an example, P is the population proportion, and by the way, P is capital X over capital N, whereas P hat is lowercase x over lowercase n. Obviously, lowercase n is the sample size and capital N is the population size. So with that being the case, since we don't have access to the population, we pick up a sample. And for that sample, we can figure out the proportion. That proportion is called P hat. Now, different samples have different P hat. So if you have a bunch of them, you can add them up and divide by size. That would be mu of P hat. What this means is we have a bunch of P hats. Where do they come from? Those are proportion of a specific sample size. Let's pick a number. Let's say n is 7. Then all possible samples of 7, we calculate the proportion for each case, and we make a note of it. When we take the mean of those, that is mu of a P hat, and that ends up being equal to P. We discuss the rest of them. We look at the sampling distribution of the means and variances as well. So this is just to repeat the question. In short, the behavior of sample proportion P hat. The distribution of sample proportions tends to approximate a normal distribution. Sample proportions target the values of the population proportion. What does it mean, target? The mean of all sample proportion, P hat, is equal to the population proportion, P.
Consider repeating this process. Roll a die 5 times and find the proportion of odd numbers, 1 or 3 or 5. What do we know about the behavior of all sample proportions that are generated as this process continues indefinitely?
First of all, repeating the process indefinitely, obviously, it's difficult. But if you do it large number of times, that is reasonably decent. So here's the graph we got. The sampling procedure. Roll a die 5 times, calculate the proportion P hat for odd numbers. For example, as you can see from sample 1, we got 0.2, sample 2, we got 0.4, and we move on with that. It ends up that according to this, the population proportion is 0.5, sample proportions are approximately normal. Let's just read on and see what's going on.
The figure illustrates this process repeated for 10,000 times. The sampling distribution of the sample proportion should be repeated process indefinitely. The figure shows that the sample proportions are approximately normally distributed. 1, 2, 3, 4, 5, 6 are all equally likely, 1 and 6. The proportion of odd numbers in the population is equal to 0.5, and the figure shows that the sample proportions have a mean of 0.5. So then mu of p hat is equal to p.
This process has to be done in infinite number of times. But 10,000 is pretty much big enough. And it may not give you exactly 0.5, but it gives you close enough answer. That's the idea. Maybe even 1,000 times is good enough. Now, as you know, there are 6 sides for a normal die, and there are 3 out of 6. That means 0.5. 3 out of 6 odd numbers, odd numbers. So you do expect a 0.5 no longer. And this actually shows that. That's the idea. So the distribution of sample proportion tends to approximate a normal distribution. That's what we have at the top. And sample proportions target the value of a population proportion. Why is that? Because the mean mu of p hat, okay, the mean of all the sample proportions, mu of p hat, we got a bunch of sample proportions. Take the mean of this group. What does it mean? Add them up, divide by 10,000. In this case, because we did it 10,000, the mean. And so that's the idea behind proportion.
The distribution of sample means tend to be a normal distribution. This will be discussed further in the following section, but the distribution tends to become closer to a normal distribution as the sample size increases. The sample means target the value of the population mean. That is, the mean of the sample means is the population mean. The expected value of the sample mean is equal to the population mean.
So mu of x bar equals mu. That's the idea which is important to understand. So with that being the case,
Example 2. Consider repeating this process. Roll a die 5 times to randomly select 5 values from the population, 1, 2, 3, 4, 5, 6. Then find the mean x bar of the result. What do we know about the behavior of all sample means that are generated as this process continues indefinitely?
in the previous example, we calculated the p hat for each case. Now we are calculating x bar. And when we look at the graph that is given, sampling procedure, so we roll a die 5 times and we calculate the mean. So for example, this is the mean for the first case, this is the mean for the second case, and so on and so forth. We add them up and we divide by how many times we did that. Again, this is 10,000 times, and that becomes a number. That number happened to be equal to mu equals 3.5. So let's go through the process.
The figure illustrates the process of rolling a die 5 times and finding the mean of the results. The figure shows results for repeating this process 10,000 times. Your sampling distribution of the mean involves repeating the process indefinitely. 1, 2, 3, 4, 5, 6 are all equally likely. 1/6, the population has the mean of mu equals e of x equals sum of x times p of x equals 3.5. The 10,000 sample means included in the figure have a mean of 3.5. If the process is continued indefinitely, the mean of the sample means will be 3.5. Also, the figure shows that the distribution of the sample means is approximately a normal distribution.
We know that the formula is e of x is summation of x p of x. So the probability is 1/6. So how you calculate this is summation 1 plus 2, 3, 4, 5, 6 times 1/6, because the probability for each one is 1/6. In other words, 1 times 1/6, 2 times 1/6, so on and so forth. You calculate it, and that gives you 3.5. That's how we arrive at 3.5. This is the process. Mu, or E of x, is summation of x p of x. That's how it's calculated. As far as what we just did for this sampling distribution, we just did the sample 1, calculated the mean, sample 2, sample 3, and now this, we add them up and we take the mean. And this one is mu of x bar. It so happened that mu of x bar also is 3.5, and it's equal to mu. Therefore, the distribution of sample means tends to be normal distribution. And the sample means target the value of the population mean. Now we're going to discuss the sampling distribution of the sample variance. The sampling distribution of the sample variance is the distribution of sample variances. The variance is S squared, with all samples having the same sample size and taken from the same population. The sampling distribution of the sample variance is typically represented as a probability distribution in the format of a table, probability histogram, or formula. At the bottom, reminding you about the formulas that we have seen for the population variance. Sigma squared is the summation of x minus mu quantity squared over capital N. And then the deviation is simply the same thing, take a root, and it's slightly different than S squared, which was the summation of x minus x bar quantity squared over N minus 1. So we don't want to mix them up.
Behavior of sample variances. The distribution of sample variances tend to be a distribution skewed to the right. 1. The sample variances target the value of the population variance. That is, the mean of the sample variances is the population variance. The expected value of the sample variance is equal to the population variance.
Okay, now it's no longer normal, and that we can see from the graph as it comes up in a moment. And it does target the value of the population variance because of this. So if you calculate the variance for each sample and then you divide by size, it gives you sigma squared, which means yes, it does target it, but the shape is not normal. So when it comes to the behavior of the variance S squared, the distribution of sample variances, remember, S squared is the sample variance, sigma squared is the population variance. The distribution of sample variances, it is not normal. It tends to be skewed to the right. The sample variances target the value of the population variance. That is, the mean of the sample variances is the population variance. The expected value of the sample variance is equal to the population variance. So I want to make sure we understand the difference that happens here when we looked at proportions and means and the variances. All of them, the sample targets the population. That's fine. But as far as the shape is concerned, variance doesn't give us a normal distribution. The other two do. Okay, that's as far as the shape. By the way, because standard deviation is the square root of this, then that doesn't target the sample standard deviation simply because there is no linear relationship. Okay, there's a square root relationship. It won't work out.
Consider repeating the process. Roll a die 5 times and find the variance S2 of the results. What do we know about the behavior of all sample variances that are generated as this process continues indefinitely?
We look at the proportion of a sample. In one case, we look at the mean of the sample. And now we are looking at the variance. We're looking at the variance. So that means, for example, the first sample gave us S squared. One notation to use that is S1 squared. That means sample 1, S sub 1. For sample 2, we could say S sub 2 squared. For sample 3, we can say S sub 3 squared, so on and so forth. And when we do that, it gives us a bunch of numbers. Now, what do we do with those numbers? We take a mean of those numbers. What does it mean? Add them up, divide by size. Size, again, is the same thing, 10,000. And that happened to be equal to the population variance, which is 2.9 roughly. And so it does target the value of the population variance.
The figure illustrates the process of rolling a die 5 times and finding the variance of the results. Figure shows results from repeating this process 10,000 times, but the sampling distribution of the sample variance involves repeating the process indefinitely. Because of the values 1, 2, 3, 4, 5, 6 are all equally likely, the population has a variance of S squared equals 2.9, and the 10,000 sample variance is included in the figure have a mean of 2.9. If the process is continued indefinitely, the mean of the sample variance will be 2.9. Also, the figure shows that the distribution of the sample variances is a skewed distribution, not a normal distribution with its characteristic bell.
We're going to roll a die 5 times, and we make a note of the result. Once we calculate the proportion, once we calculate the mean, and finally we calculate the variance. We do it again and again and again and again. And in all cases, when we figure out the proportion for each sample, we add them up, divide by size. When we find the mean for each sample, we add them up, we divide by size. And remember, the size in all cases is 10,000. Why 10,000? Because 10,000 is a large enough number that you can figure out, well, it's almost indefinite. And finally, we do the same thing for the variance. So we roll a die 5 times. We calculate the variance for those 5 numbers that show up. That's one sum. We do it again and again and again. And we get different answers. We add them up. We divide by the size 10,000. It happened to be the variance of 2.9. That is equal to sigma squared, because we are saying the population has a variance of 2.9. And so with that being the case, they end up being the same. Well, let's calculate the standard deviation, sigma squared, for what? For this case in general. Now, how do we calculate that? Let's go with the formula. Everybody remembers for discrete random variable, there are 2 ways to calculate sigma squared. Summation of x minus mu squared times p of x, or square x multiplied by p of x, and then subtract mu squared. Now, what do we mean by this one? It's easier to calculate than this one. The numbers are 1, 2, 3, 4, 5, 6. So 1 squared plus 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and then times 1/6. Minus, we already have calculated mu from the previous page, and we know it to be 3.5 squared. The math will give us 2.9167. Remember, it's being rounded here. Okay, the reason is 1 decimal because of the methodology that the text uses, just 1 decimal, but I like to show you with more decimals. So the point being, theoretically, when we follow the formula, we end up with 2.9167 as far as the population variance sigma squared is concerned. And when we calculated the mean of those variances for the sample of 5, we ended up with the same number. That shows it targets it. All right, so having said that, let's look at the synopsis of this and we move on. An estimator is a statistic used to estimate the value of a population parameter. Unbiased estimator. An unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean. You really want to pay attention, that has a mean. All of them have a mean that is equal to the corresponding population parameter. For example, proportion, we use p hat. Mean, we use x bar. Remember, that means, and variance, we use s squared. That means the population proportion p, what is the point estimate, or an unbiased estimator is p hat. These are called point estimate. Point estimate. For what? P hat is the point estimate for P. X bar, point estimate for mu. S squared, point estimate for sigma squared. So this one for P, this one for mu, this one for sigma squared. Although standard deviation, it's not targeting as variance. Here's the thing, biased estimate, but we use that as a point estimate. In other words, these statistics are biased estimators. That is, they do not target the value of the corresponding population parameter, median, range, standard deviation, S. But for standard deviation, when we look at problems to solve, we do use S as a point estimate anyways because we don't have a choice. And finally, why sample with replacement?
When selecting a relatively small sample from a large population, it makes no significant difference whether we sample with replacement or without replacement. Sampling with replacement results in independent events that are unaffected by previous outcomes, and independent events are easier to analyze and result in simpler calculations and formulas.
It's important to understand the concept of independency and how important it is in statistics.